Hey everyone. Now, after going through basically the study design and the basic assumed data generating process, as well as our estimation strategy for this specific study, we're going to move on to actually implementing this design using the DeclareDesign package in R. And there are a couple of steps that kind of follow this MEDA outline to kind of declare research designs that you've read about in the Blair 2019 APSR paper. And the first step in DeclareDesign is to ultimately set up the population as well as random assignment and kind of the basic data setup. Okay, and the way to do this is as follows. And there are two steps that I'm going to show you here. Of course, we're first loading tidyverse and DeclareDesign, and then there are two parts that we add to this design declaration. We're going to basically save our design in an object called design, and the first command that we start with is declare underscore population. And there are a couple of basic features that we can set up here. We will set the sample size to 1500 as we talked about, and then we have basically one pre-treatment covariate, which is party identification, and we have one random assignment, which we're going to declare in a second. Okay, the first thing is to set the pre-treatment covariate as an exogenous factor. We will set this as a 3-category variable where we sample basically with replacement with equal probabilities, either -1, 0, or +1. Okay, and we will later recode those as Republican, Democrat, or independent party identification. Of course, these are 1,000 draws, and again, we're making kind of a simplifying assumption here that Republicans, Democrats, and independents have equal sizes. About 33% of those 1,500 are in each of those groups. Of course, we could explore variations or the effect of imbalance in that regard as well by kind of changing these parameters between design calculations. Another parameter that we're setting is the gamma parameter that I mentioned in the when I kind of introduced the assumed data generating process. Note here that I'm just for illustrative purposes, I'm setting this gamma parameter as equal to 1 just to be able to show you the result of each of those steps of the design declaration. Later on, we're going to run the same code, but then we're going to basically specify varying levels of gamma in order to analyze our design for varying effect sizes of that treatment. Okay, for now we're just assuming it's 1 just in order to be able to show you each individual step and what is actually going on kind of under the hood as you add layers to this design declaration. Okay, so we're going to leave it at that. Then we have our error term epsilon, which is just 1,500 draws from a random normal distribution, centered at 0, of course, standard normal. So this is declaring the population. All the kind of exogenous variables are basically in there, and then the second component is declaring the random assignment, right? So these are the treatment conditions that we're assigning. Okay, we have 3 different treatment conditions. One control, one positive, and one negative. And importantly, we're taking into account that treatment assignment here is blocked by party identification. So this is something that was part of the design. Random assignment was not completely, fully randomized across all observations, but rather randomized within party identification blocks. To increase power, essentially. Okay. So after setting up this basic framework, we can then kind of look into this design object and examine what this object actually kind of looks like in one iteration. Okay, and the way we can do that is we can use the draw underscore data command, which basically is just it just allows you to kind of look at one draw from that design with the specifications that you set up. What would one sample data set look like that is simulated based on that assumed data generating process? Okay, so all we're doing here is we're taking that design, we're drawing one data set, which will be basically, you can think of it as one realization of that experiment. 1,500 observations, and assume, given the specifications that we set up, what would that data set look like? And we're just printing this as a tibble, and we see we have an ID for each observation. This is 1,500 observations. We have party identification, which is -1, 0, or 1, as we specified. We have our gamma, which is just constant at 1. We have our epsilon, that's the error term that we don't observe, but that is part of our underlying data generating process. We have our assignment variable, which is called z, and then we have another additional information for the conditional probability of z, which is just equal because we have basically equal random assignment across blocks that are also equally divided. So the probability for each treatment group is just 0.33. Okay. So this is the first step, declaring the population and the random assignment. Okay. Now, let's see. Okay. The next step is kind of an intermediate step. We have to create some additional variables. Specifically, we have to kind of turn the assignment variable and the party identification variables into variables that we actually want to work with as part of, given our kind of estimation strategy, right? So if you look back in this setup, our treatment assignment ranges from 1, 2, and 3, and our party identification is -1, 0, and 1. Of course, ultimately, we want dummy indicators, dichotomous indicators for treatment assignment and party identification. Okay, so in order to do that, we have an additional step, which is where we use declare_step, and we use the fabricate function, or fabricate. It's part of the fabricate package, which allows us to kind of specify additional recoded variables as part of the design declaration. Okay, we have one indicator for bad as the negative treatment, which is basically just a dichotomous indicator for our treatment z, the assignment variable being equal to 1. We have good, so the positive treatment for 3, z being equal to 3. We have a Democrat indicator for PID being equal to -1, and we have a Republican indicator for PID being equal to 1, right? So now we have 4 dichotomous indicators for true partisanships, where independents are the reference category, and for the negative and the positive treatment, where the control condition is the reference category. Okay, so if we now look at the same data set, we again draw data and look at that tibble based on that design. Note here also, I should have mentioned this, we take our old design object that we specified previously and just add this declare step on top of that, right? We're adding these as layers, similar to in ggplot where we add layers to a plot, right? You can think of this as a similar kind of setup to specify these designs. Okay, so we have the same data frame. Well, different draws, of course. These are different random draws. The numbers here are different, but the structure is the same. We just have additional variables: bad, good, Dem, and Republican for the respective kind of recodings of our treatment assignment variable and our party identification variable, right? And you can go through here. Party identification being equal to 1 is equivalent of Republican. -1 is Democrat, and 0 is of course the reference category, so both Dem and Rep is equal to 0, and the same for the positive and negative treatment. Okay, we have 1 is equal to the negative treatment, 3 is equal to the positive treatment, 2 is equal to control, so both positive and negative treatment indicator are equal to 0. Okay, all right. After creating these additional variables, we can move to the next step, which is declaring potential outcomes, right? So this is now where our kind of data generating process that we assumed that I presented in the previous video comes in. We're now basically declaring, kind of assuming we, the fundamental problem of causal inference didn't exist, and we actually were able to, compute all potential outcomes for each observation. And that's what we're doing here now, right? We're declaring potential outcomes. Y, that's our outcome variable. And this is just translating the data generating process that I outlined in the previous video into R, right? We have a negative -1 times Democrats, or a negative coefficient for Democrats, positive for Republicans, negative coefficient for the negative treatment, positive coefficient for the positive treatment of equal size. So this is symmetric. Gamma is the coefficient that we're going to vary between 0.1 and 1 to look at different sizes of this kind of treatment effect relative to the partisan differences, which is, just for simplicity, being equal to -1 and +1, right? That's the setup that we talked about before. We have this motivated reasoning effect, where the effect of the negative treatment cancels out for Republicans, and the effect of the positive treatment cancels out for Democrats. And we have the ceiling effect for Democrats and for Republicans for the positive and negative treatment, respectively. Okay. In addition, we're specifying here conditions, which basically just tells are that the conditions for which we want to compute these potential outcomes are good being equal to 0 and 1, and bad being equal to 0 or 1, right? So those are the potential outcomes that we want to compute now. Okay. After we've done this, we can again draw a data frame based on that design that now has our declared potential outcomes. We can again look at this as a table, and I'm just removing some variables just to make it fit on the screen. Essentially, what we still have, what I'm omitting is some of these variables that we're not going to use: the PID, gamma, epsilon, z, and z conditional probability. All those we're not going to use. We're going to use the recoded variables that we have down here. So I'm just plotting those. And this is what this looks like. We have our ID, we have our indicators for the positive and negative treatment condition, we have our pre-treatment covariates for Democrats and Republican, and we have three potential outcomes. One for the control condition, where good and bad is equal to 0, assuming this data generating process. Then we have one for good being equal to 1 and bad being equal to 0, so that's the positive treatment condition, and for the negative treatment condition. Okay, so basically this is now the simulated outcome variables based on this data generating process and the covariates that we specified previously, and of course taking into account our epsilon, which is the error term that we specified. Okay, so these are now the potential outcomes. Of course, given the fundamental problem of causal inference, we're not observing all of those potential outcomes, but they, in the hypothetical scenario where we could observe them, we can use them to specify our treatment effects of interest, right? And that's what we're basically going to do now in this step. We're declaring the estimands, which are basically the quantities about the population that we're trying to make inferences about. Okay, so what we're going to do here is we're going to focus on 6 different estimands that we want to examine the power for. The first 2 are basically just the average treatment effect of the positive and the negative treatment, which is just the difference, the average difference between the treatment condition and the control condition for the positive treatment and the negative treatment. We're doing this now here using the declare_estimand command. I should always emphasize that. So these are the basic average treatment effects, essentially among independents, the effect of the positive and negative frame in the survey experiment. And then we have these 4 different interaction terms two of which, the Democrat bad interaction and the Republican good interaction, that's the indicator for this ceiling effect that we talked about. And the main interest is here, of course, the two treatment effects between how Republicans respond to the negative framing and Democrats respond to the positive framing. And the idea here is, of course, that these would cancel out, they would disregard that information. And so these are therefore the estimands are therefore the true gamma as well as the negative value, the negative true gamma for Democrats, okay, given the data generating process and the setup that we have so far, right? So based on that, if we add this to the design, we can also, rather than draw data, we can now draw estimands. And the estimands are now basically, given the data that we have and given the potential outcomes, and the specification of the estimands that we want to basically learn about, we can now compute the true, if the fundamental problem of causal inference didn't exist and we could observe all potential outcomes, we can directly compute these average treatment effects as the differences between the actual potential outcomes for for the negative treatment, for the positive treatment, and for these respective interactions. Okay, so these are actually based. So the two average treatment effects are actually based on the differences between those potential outcomes, and these are actually based on the true gamma that we're using in this scenario. Okay. The next step is to reveal the potential outcomes, and this is kind of the step where, of course, in the real world, we don't observe all potential outcomes. We just observe realizations depending on the actual treatment assignment. And so this step basically reveals out of the potential outcomes that we kind of simulated now, we will, for each observation, assign the potential outcome that is kind of appropriate for that actual treatment assignment and the actual covariates that is realized. Okay, so basically what we're going to do is we will just use the declare_reveal command, which will reveal the actual dependent variable y, and basically based on here we have include list good bad, which is based on those potential outcomes for the different treatment conditions. Okay, and so essentially what we're looking at is basically we have the potential outcomes for each observation, and we know that, for example, the first observation here is in the control group and is a Republican. So the predicted, the realized potential outcome is, of course, the outcome that is in the control group. So that will be the revealed y that we actually observe, right? Another observation here, this is, for example, someone in the positive treatment. So that means the potential outcome that is realized is the one where good is equal to 1. So that's this potential outcome. So the value that is then added in the y column is then that respective potential outcome for the specific treatment assignment or treatment regime. Okay, same here for people, respondent 8 who's in the negative treatment or negative framing group, so that the respective potential outcome is minus 864, and so that's the outcome that is then realized. Okay, then in the next step, now we have the data generating process, we have our potential outcomes, we have the underlying estimands that we're trying to make inferences about, assuming the fundamental problem of causal inference didn't exist. Now we have a declared, a revealed actual outcome that we observe given the data generating process, and now we're going to specify the estimator that we're using to learn something about the potential outcomes and the estimands that we specified. Okay, and we can do this using the declare_estimator command. So we're specifying a basic linear regression with these parameters that we already looked at, the interaction terms between partisanship as a pre-treatment covariate, and the treatment assignment positive and negative framing of the handling of the COVID-19 pandemic. We're using robust basic OLS with heteroscedasticity, robust standard errors, and the terms that we're interested in are, of course, the average treatment effects and these interactions. And ultimately, these are then matched to the estimands that we specified previously, right? So each of those parameters that we're estimating are then kind of matched to the estimands that we're interested in that we specified previously, right? And that comparison between our estimator, what we're getting out of the model, and the underlying estimands based on the true data generating process and the the unobserved potential outcomes, that will be the comparison that will then help us kind of specify, for example, whether there's any bias in our estimates, whether and what statistical power looks like, what type S, type M error looks like, and so on. Okay. Based on this, another useful step here is at this step, after we specified the estimator, we can use the draw estimates command, and that basically does the same kind of procedure that we did previously. We kind of simulate one hypothetical data set using this data generating process, and then use our estimator that we specified, and then draw estimates will basically provide you with an overview of what these estimates look like, right? So this is basically, these are now the regression coefficients for the specific terms that we wanted to extract, and we already attached which of these estimates the specific regression coefficients should be matched to, right? The average treatment effect of bad and good, or the positive and negative frame, and the respective interaction terms. Okay. Now this is basically complete. Now we basically declared the entire design up to the point where we have the estimators, we have our estimates, and we can basically compare what our estimator gives us to the true underlying data generating process. Of course, what we want to do is we want to repeat this design declaration for varying values of gamma, right? So in the illustration that I showed you now, I just set gamma as equal to 0, but the question ultimately that we started with, that we wanted to answer, was to what extent are we able to recover or identify this motivated reasoning effect for varying levels of, or for varying effect sizes of this treatment, right? So depending on how effective this treatment might be in shifting attitudes, are we able to then recover this motivated reasoning to the extent to which Democrats and Republicans disregard counter-attitudinal evidence regarding the performance or the government's performance in handling the COVID-19 pandemic, right? So how do we do this? One thing we have to do is we kind of have to run all this code again. Instead of setting gamma equal to 1, we set gamma equal to a parameter that we're going to kind of supply in multiple iterations, right? So we set gamma equal to gamma as a placeholder, and we'll basically plug in different values for gamma in a second. And specifically, we're doing this using the redesign command. So we're I'm specifying the entire design the way we did it here, step by step. I omitted the code for the remaining steps here. The only thing that I changed was adding this gamma. And then I take that design object and then use the redesign command to basically kind of repeat this design, this whole procedure, for varying levels of gamma. This gamma is now ranging from 0.1, as I said, to 1, which is the maximum assumed effect size that I talked about previously. And basically we go through the same procedure, all these steps that I mentioned previously, with varying levels of gamma. Okay, and that's what the redesign command ultimately does, right? After we did this, we can again draw estimands for well, we could also draw data sets based on each of these designs, But essentially, what is more interesting is to draw the estimands for each of those designs. And the way this basically looks like is if we do this for the redesigns or the designs object, which basically consists now of a set of 10 different designs with varying levels of gamma from 0.1 to 1. We can now basically go through the entire procedure and compute these estimands and as well as our estimators and basically examine how both our estimators change and our estimates change, and then how power and everything is affected by changing these parameters, right? Rather than changing gamma, we could also change the sample size here. We could change other parameters. We could change factors related to the sampling procedures and so on, or the treatment assignment regime and so on, right? So there are basically a wide range of possible scenarios that you could explore and how they ultimately impact your estimates, okay? All right, so now we're at the point where we have not only one setup of that design, but we basically have 10 different scenarios of the same design with varying levels of gamma. And now what we're going to do is we're going to, for each of those 10 scenarios, we're going to simulate 1,000 data sets, 1,000 realizations of that experiment, look at the estimands, look at the our actual estimator, and compare basically or examine the extent to which we're able to, in our case, we're just focused on power, we're able to reject the null hypotheses that each of these parameters is equal to 0 based on the estimator that we're actually using, okay? So all we have to do in order to do this is we have to use the command simulate_designs based on our designs, which now again combines 10 different scenarios for varying levels of gamma, and each of those now will be simulated with 1,000 simulations, okay? And then after we did that, we can look at our simulations, and we can now we see this is a large data frame, 60,000 observations, which basically takes into account a couple of different variables. We have different iterations. We have basically 60,000 because we have 10 different scenarios. For each scenario, we have 1,000 simulations, and for each simulation, we have 6 different parameters, or 6 different estimands and estimators, right? So or estimates. So for each of those scenarios and each simulation, so that's 10,000, we have one time the average treatment effect for the negative frame, the average treatment effect for the positive frame, and 4 different interaction terms. So that's in total 60,000 quantities essentially for distributed among the scenarios, or clustered by scenario, by simulation, and the estimate essentially, okay? So for each case, of course, we have the estimate that's again based on the true data generating process and the potential outcomes that we kind of are in reality not observable, but in our simulation we actually know what the potential outcomes would be, and our estimate. And so based on that comparison, we can, as I said, look at bias and so on, right? So the next step is to prepare this large data frame for plotting. And this is relatively straightforward. I'm just creating a summary data frame where I take the simulations that we created so far. I'm grouping them by gamma and by estimate label. So in other words, by the scenario that we're looking at and the type of estimate that we're looking at. And then I will compute the power by looking at the average p-value, or the average, so p-value smaller or equal to 0.05 is basically true for all p-value. The variable is of course not included in the output, but essentially one column in this data frame is the p-value for the specific estimator, for the specific estimate in that given scenario. So we're basically just checking whether this is equal to smaller or equal than 0.05, and then computing the average, which means basically the proportion of times we're rejecting the null hypothesis for that specific parameter, right? So that's ultimately that will be equal to the power that we want to compute. We know the true population effect is not equal to 0, so the null hypothesis should be rejected, and so this tells us the proportion of times that the null hypothesis, the false null, is actually rejected. Okay, so that's the power. And we can also look at the average estimate as just the if we wanted to look at bias, for example, we could use that. Then I'm just creating an additional factor variable based on the estimand underscore label. So that's the the indicator for the different estimands, and I'm just creating some nicer labels for the plot that we're going to have on the next slide, right? So this summary is then, of course, a 60 by 5 tibble because we're combining now all 1,000 simulations, right? So we're left with 60 for 6 different estimands and 10 different scenarios. So that's 60 by 5, and we have our power and we have our mean estimate. Okay. And the last step, step 11, we plot our results. All we have to do is create a ggplot call with our summary df data frame. Our aesthetics are as follows. We have gamma on the x-axis, that's the varying parameter that we looked at. We have our power on the y-axis. We're grouping this by the label variable and assigning different colors and different shapes for the label. And then there's a bunch of other additional commands to make the plot a little bit more pretty. We talked about visualization before, so I'm not going to go through them step by step. But essentially, we will look at a line. Different points for each level of gamma connected with lines and comparing each of those different estimates that we talked about. The easier way is probably to just show you the graph. This is the output that we get when we execute this command, run this command, and what we see is now statistical power, as I said, on the y-axis. The kind of the acceptable level of power that we kind of are looking for is 0.8. We have on the x-axis gamma. As I said, 1 was equivalent to a hypothetical scenario where the treatment effect is just as large as the partisan differences between independents and Democrats or independents and Republicans, right? So a quite substantial large effect. And then we have kind of 3 different clusters of estimates. On the one hand, we have the red and blue here. These are the average treatment effects of the positive and negative frame. And as I mentioned, we're assuming that the positive and negative frames have kind of symmetric effects. We could, of course, assume that they're varying in size, but essentially that would just, shift this line to one side or the other, but the important point is how for these varying levels of this treatment effect, power of course decreases as our gamma approaches 0, and we can see given this framework that we set up, up to down to a gamma of around 0.3, we have a sufficient power of around 80% or just under 80% to basically identify the treatment effect of the main treatment effect among independents, essentially, right? So if the effect of the treatment, both the positive and the negative treatment, is in size about 30% of the difference between independents and Democrats or independents and Republicans in terms of the evaluation of the government's handling of the coronavirus pandemic, then we have sufficient power to identify those main treatment effects, right? The next two parameters that we're looking at is the interaction between the negative frame and Republicans and the positive frame and Democrats to examine this motivated reasoning component. And if we look at that, we see we have sufficient power to identify or to recover that effect for effect sizes up to about gamma equals between 0.5 and 0.4. Okay, so around 0.45. Okay, so if the treatment effect is, if the effect of the treatment basically shifts people's attitudes, about 50% of the difference between in the evaluation of the administration between independents and Democrats or independents and Republicans, then we have 80% power. Under those assumptions, we have sufficient power to identify that effect, so to speak, right? So that's also sufficient for kind of a reasonable range of effect sizes. We will have enough statistical power to basically identify this motivated reasoning or pattern, as well as the main treatment effect of this positive and negative frame. For when it comes to the ceiling effects, the kind of the cross interaction for Democratic respondents and the negative frame, and Republican respondents and the positive frame, power is much lower, and we would only be able to kind of recover these effects for very large treatment effects. But on the plus side, from our perspective, is that these ceiling effects are ultimately not the main interest of our analysis, so we're quite fine with not being able to recover these interaction effects fully. Okay. That's all. That was a lot of code and a lot of steps. We went through 11 steps to set up this design, but kind of once you kind of go through each step or go through these commands step by step and see how they kind of build onto each other and kind of go through all these components of the MEDA declaration of research designs. It's fairly straightforward. It takes a little bit of time to get used to those commands, but it's an incredibly powerful framework, and it makes design calculations and power calculations and planning experimental designs so much easier, and also it makes it so much easier to also share your design with other researchers, communicate the key components of your design, and explore how changing specific components, for example, the treatment assignment, what is the effect of blocking versus not blocking, and so on. There are countless numbers of design specifications where you can directly explore the effect on your estimates, your estimate, your power, your bias, and so on. Right. So it's an incredibly powerful tool, and I can only recommend you to start using it for your own research as well. The last thing I should say, I wanted to add a link. I'll add that later on. But there is a great library of design setups on the DeclareDesign website as well. Let me just Google that real quick. If you go on DeclareDesign.com, let me move myself again a little bit. There's a ton of really good resources here as well. You can go through the kind of the vignettes to kind of go through the steps of setting up your research design here as well. So feel free to go through those explanations as well. They're really well documented. But the one key point that I wanted to show you, make sure that you've seen it, is the design library. That is really useful. For a lot of kind of standard designs, you can directly, you don't have to kind of go through every step individually and program it in DeclareDesign, from scratch. But you can basically use these pre-designed, standard designs, like a binary, factorial design, multi-arm design, and so on, right? So they're usually vignettes, explanations, there's code. So a lot of the designs that you might be thinking about, you can already use those templates and directly get started. All right, this is it for this week. I'm really looking forward to our Q&A session this week.